Okay, so today we are going to talk about diffusion equation, diffusion approximation. So it's really the follow-up of last week's course. To illustrate the presentation, the course today, I chose this artist, Mark Mawson, who is taking pictures of diffuse material, like diffuse dyes in water. So he has very nice picture, and it's very related to diffusion. Okay, I think it was really relevant for that. Actually, he reversed the picture, but he found this effect by looking at milk. When you pour milk in your coffee, you have the same effect, the same type of pattern. Okay, but he reversed the image. So actually, the liquid comes from this side here and drops inside the other liquid. So there are very nice pictures. He's doing also pictures for advertising products. So, very interesting artist. Okay, so I hope you get a chance to go over last week course, like I asked you in my message. But I will review rapidly. I will summarize what we learned last time. Okay. So that was really fundamental concept that we learned last time. So if you remember, let me turn on this screen because this one is not complete. So we have been. So I introduced a number of quantities that are useful in this domain. So you remember that everyone is around the specific intensity. Okay. So the specific intensity actually is defined from the radiative power. So this is the power that is radiated from point R in direction U over a solid angle delta omega and the frequency range d omega, d small omega, okay, through an aperture which has a section ds, okay. So that's the power that is radiated in that direction, like in the picture here, okay. And L, so the L, which is the specific intensity, represents the density, the power density, okay. So that's the power per unit surface, per unit omega, per unit frequency. Okay, so that's really at the core of the radiative transfer equation. That's the quantity that the radiative transfer equation deals with. Okay, and from there, from this quantity, you can define another set of quantities. The first one is the radiative flux vector here, which you see well. So, so Q here is a vector. Okay, Q is defined as the integral over the full space of L times U, the direction you are looking at, over the omega. So you integrate over all direction, and you look at how much L is that measures the anisotropy of L. Okay, if L is completely isotrope, if it is the same in all direction, then this quantity is zero. Okay, so it measures some kind of direction of propagation of the diffusive field. So I show you here, for instance, you remember when you look here at the diffuse light here on this picture, you see that there is some direction. It's not completely isotrope. There is an anisotropy in that direction. Okay, so Q measure actually this flux vector, the direction of the anisotropy of the diffuse light. Okay, so that's very important for the following, so keep that in mind. Okay, and the last quantity is simply the integral of L over all direction. Okay, so that's the energy volume density of energy which measure how much energy is diffused inside the system, okay? Times 1 over C. So we saw that last time, right? This C is coming here. Okay? So that's the starting point, that's the starting quantities that we have been using last time. So what do we do with that? We define a certain number of characteristic length. The first one is related to absorption. How much of the energy is absorbed is given by a characteristic length, which is the absorption mean free path, LA, which is 1 over mu A, where mu A is the coefficient, the absorption coefficient. So this is absorption by the material itself. Okay. The second quantity that we define is the scattering mean free path. So that's the amount of light which is lost relative to the ballistic light. Okay. So this is lost on the characteristic length, which is the scattering mean free path, LS, which is 1 over mu S. Mu S is the scattering coefficient. Okay. And there is an expression, a simple expression in the case where you have a dilute sample, which is 1 over n, the density of scatterers, times the cross-section of one scatterer. Okay, so in the case of a dilute sample where the scatterers are far from each other, you can approximate the scattering mean free path by 1 over density times scattering of one scatterer. Okay, so the total scattering is n times the scattering of each scatterer. Okay. If you remember, we talked about the albedo also last time. So the albedo is a simple parameter to measure what is the proportion of light which is scattered relative to the proportion of light which is absorbed. Okay, so those are two different phenomena. They have two different characteristic lengths. Okay, and the albedo measures how much is scattered, how much is absorbed. So if A is close to 1, that means that essentially the medium is scattering, like milk, like white paint. Okay. If A is close to 0, that means that mostly you have absorption in the medium. Okay. So those two parameters can be measured actually, and it is used in medical imaging. You can actually image the body by using like ultrasound, not only due to scattering but also to absorption. So two parameters that can be helpful in imaging for instance, the biological tissues in the body. Okay, so that's the albedo.
Patrick,
yes.
Can you put the screen down? The light is.
I know, but so it doesn't come down. I don't know why. That's the problem. Yeah, it works once and then it never worked again.
Because the light reflects from there.
Yeah, so it's not good. I have no way to change that, except to use this screen. I mean, you can come closer. I don't think they will not come because so you can come closer and watch from here. Yes, there is the light from the projector. Is it better?
Yeah.
Yeah, you don't have the specular reflection. Okay, so if you remember, we defined also the phase function. That's a long time ago actually. The phase function is the probability density of scattering from direction u prime to direction u. Remember, p of u prime. Okay. This phase function will be very important in this course, so keep that in mind. So that gives you the scattering diagram that we learned at the very beginning. Okay. So it's a probability density. Okay. It's normalized so that the sum of u prime. No, that's not true. So it's the sum of p. The sum of p simply is 1, not u prime. There is an error here. Okay, so P describe the scattering diagram actually due to the medium, not only to one scatter but for the complete system, all the scattering medium. Okay, and what was important, and I think that's my mistake here, is that we define what is called the anisotropy parameter, the small g here. Okay, which integrates UU prime times P, so that's why here it was a mistake. Okay, so this normalization, but without, I mean, by multiplying by this quantity, you get G here. So you remember that P, in general, P does not depend, that depends only on the product UU primes on the cosine theta. Okay, so the difference between the two angles, whatever their direction, it's only the cosine theta that matters. So in that case, you can write it like that. So it's 2 pi sum of from -1 to +1 of cosine theta P of cosine theta d cos theta. Okay, so that's why we call it the average cos theta. Okay, so it's you see it's taking the probability density times the cos theta here, and that gives you G. And if you remember, G gives you how much the scattering is in the forward direction or isotropic. So isotropic scattering means G is close to 0. Forward scattering means G is close to 1. Okay, so this parameter is very important. Okay, because although light can be scattered, it can keep the memory of the incident wave. Okay, so G measures this memory effect, and from this quantity we define the transport mean free path. So LT or L star, which is actually the scattering mean free path divided by y minus G. Okay, so if G is close to 0 for isotropic scattering, LS and LT are the same, and if G is close to 1, LT, so the characteristic length of the transport mean free path, it can be much larger than LS. Okay. So you remember, LS is the distance after which I lost light from the ballistic beam, or from the ballistic photons, okay? And LT is the transport mean free path, so it's the distance after which I lose the direction of propagation, the initial direction of propagation, okay? So I don't see the source anymore. Okay, any question on this summary? That was last week course. I mean, that was actually the starting of the last week course, and we end up with the master equation, which is the radiative. Hello, hi. We just started to review what we discussed last week. Sit here because you won't have the reflection from the projector. It's better. Okay, so from there we wrote this very special equation, the radiative transfer equation, which is an integral differential equation, differential and integral, okay, which describe the transport of the specific intensity or the luminance L, okay. So yeah, nothing to say special, okay. So you have a time derivative for the luminance here, times the derivative of the nabla of L times U. Here you have mu S plus mu A, so that's actually the total loss due to absorption and scattering, okay, times L. And we have this term here, which includes P, okay, this function that I mentioned before, okay, the phase function P, okay, comes into the picture here, okay. So you remember we said that actually there is a loss of luminance, of specific intensity due to either absorption or scattering, but there is a gain because part of the light is scattered back into the same direction as the initial direction. Okay, so this contribution here, which is given by this p u prime, actually is a positive contribution, like gain. I mean, we have some extra light coming back into the beam. Okay. So with that, we are all set. That's the summary of last week. And what we are going to do now is to go a step further in the approximation, because this, by the way, this equation is quite difficult to solve. It was solved for some specific cases, as I mentioned last time, but it's quite a complicated equation. But we're going to simplify it for a specific case. So that's the diffusion equation, diffusion approximation. So what is the diffusion approximation? That's actually the approximation when all the energy is carried by the diffuse components. You remember, the intensity was the sum of the collimated intensity, the ballistic light, plus the scattered light. Okay, so you have light, the direct light, and part of it is scattered. Okay, after some distance, this term completely disappears on the scale which is LS, the scattering mean free path. Okay, after a few scattering mean free paths, you can forget about this term, and mostly the light is scattered. Okay, and that's the regime that we are going to consider here. So we are in a regime of strong scattering. This term is ignored, and the energy is carried essentially by the diffuse component, the scattered light. Okay, and we will consider a situation where the spatial and temporal scale are large compared to not the scattering mean free path, but the transport mean free path. Okay, we are looking at sizes much larger than LT. Okay, and times larger than LT over C. Okay, so now our characteristic length is not anymore the scattering mean free path, but the transport mean free path, which can be longer than the scattering mean free path. Okay? So in that case, the radiative transfer equation, I will show you that it can reduce to another equation, which is called the diffusion equation, which is a much simpler equation and more tractable equation to solve. Okay? So in this chapter, I will show you that on large scales, spatial and temporal scales, okay, the radiative transfer equation can be transformed into a transport equation, which describes not anymore the specific intensity, but we are going to consider the evolution of the energy density. Okay, you remember energy density, this is the integral of L over all space, all direction of space. So we are going to consider a transport equation for this quantity. You see, oh, that's something I wanted to point out here. If I go back here, you see here, this quantity here depends on u, depends on the direction, okay? The specific intensity can be different for different direction. Same thing for the radiative power, that's the power radiated in one particular direction. But if you consider the flux vector here or the energy density here, you see that they don't depend anymore on u. Okay, they are independent on the direction. Okay, although q is an integral over all possible u, okay, and it's a vector, it's not related to u. Okay, there is no u variable. Okay, so that's a very important point to keep in mind. So that's what I wanted to say here. So this quantity that we are going to consider here, the energy density, does not depend anymore on u. Okay, which really will simplify the equation. And the transport equation for energy density, we'll see that it's very similar to the heat equation. The diffusion equation is the heat equation, okay, the equation for propagation of heat. Okay, so actually they are identical. Okay. So this transport equation is the diffusion equation like the heat equation. And what we are going to show is that the radiative flux, okay, the energy which is the flux of energy, okay, the flux of the radiation, I will show that this is proportional to the gradient of the energy density. Okay, so it's like for the heat equation, okay, the variation of temperature, okay, the flux of the particle or the temperature, if you want, is proportional actually to the gradient of the temperature itself. Okay, so that's the simple concept of the diffusion equation that we are going to demonstrate today. And the proportionality constant here is called the diffusion coefficient, which is a very important characteristic of the medium. It's a macroscopic characteristic of the medium to describe diffusion. Okay? So that's the outline of today's class course. Okay, so what I will show you actually is that we are going to do a kind of expansion of this function p of u prime. Okay, we are going to show that you can consider the zero order of the expansion, the first order. Okay, so the zero order will give us an equation of energy conservation, and the first order, this is called the P1 approximation. Okay, will give us actually the equation that we are looking for, and will bring us to the diffusion equation. So I will detail that, and I will show a specific example of how we can use the diffusion equation in the case of a slab. So you propagate light through a thick slab of scattering medium, and what we can calculate out from that. And then I will finish with a very different approach, which is called the random walk. Okay, but actually they are completely equivalent. But this one is really illustrative of the way light propagates in a diffusive medium, and very useful actually to do a numerical simulation to describe this media. So the P1 approximation that I'm going to discuss here, that's really the starting point to establish the diffusion approximation and the diffusion equation. Okay. So we are going to take the radiative transfer equation. We are going to take successive moments of this equation. Okay. So let's start with the zero order. Okay, the zero moment of this function. Okay, you know this concept of moment, yes? You have let's say a probability density, a function which is a probability density. Okay, the first order is like x times this function. Second order is x squared times this function, and you integrate over all space. Okay, that gives you the deviation from the average, you get the variance. Then the higher order will tell you about the tails around this average. So that's what we call moments. Okay, so that the successive moments describe more and more precisely the tail of the function. And calculating all the moments actually gives you all the information on the probability density. Okay. So let's start with the zero moment. That's the simpler thing to do. Okay. So I just, for you to have it in mind, I put here the energy density the flux vector here, okay, and I don't know whether there is a line here, but this is the radiative transfer equation, just for to have it on the same slide, okay. Okay, so I take the radiative transfer equation, this equation here, and I integrate it over all space, okay, so that the zero moment I don't multiply it by any vector, any parameter, okay. So just taking the integral of this function. So first term, so I do it on this screen, it's easier for me. Okay, so taking here the integral over the time term, I can take the time out. Okay, so here you recognize the energy density. I do it step by step, so I spent a lot of time to prepare this course so that every step is clear for everyone. It's clear for me and then for you, I hope. So first term, you recognize here the energy density. Okay, second term here, so you integrate again over all direction d omega u delta gradient of L. Okay, so that's a specific and a complicated term that we will have to deal with later. Okay, and in the second part of the equation, you have minus mu s plus mu a integral over space of L. So again, this is the energy density plus a last term here. So this term here. So if I integrate this term over space, over all direction of u, so the integral here is integrated over u prime, okay, d omega prime, but you take the integral over all u, all possible u, okay. This integral can be put inside, so you integrate first p of u prime, d omega, okay, and this is 1 by normalization, okay. So this normalization gives you 1, and you are left with this term. So you are left with mu s times L of omega here. Okay, so I think I wrote it for that. Yeah, so using the normalization here, I get actually, I can remove actually this function, and again, I end up with the energy density. Okay, it's clear? I do it again, or it's clear? Okay, you take the integral, you integrate here over all u, possible u. Okay, then you can permute the integral, so it's going to be integral over all u of p u prime d omega. Okay, by normalization, this is 4 pi, not 1, it's 4 pi. Okay, so the 4 pi will cancel here. Okay, so this term disappears, and you end up with you end up with mu s times integral of L d omega prime, and this is the energy density here. Okay, mu s. Okay, so you see something funny here is that mu s minus mu s, so actually the scattering component disappears. Okay, so if we write this equation from the definition of the energy density directly, you get this equation. So the time derivative of the energy density u plus so here I just take the nabla out here. Okay, so the integral of u L is q, so it's nabla of q. Okay, so that's writing this expression in a simplest way. Plus this term cancel, you have mu a times c, the velocity here, times the energy density. Okay, so you end up here with an equation which is actually energy conservation. Okay, only on u and q. Okay, so you have a relation between u, q. U is also here. Okay, so So why this is energy conservation? Let's say we consider the stationary expression, we ignore the time variation here, the steady state, the CW regime. What you get is that the variation of Q, of the flux, okay? So if there is a flux of energy, this is because you have a source of loss here, you lose some energy, and the loss is due to absorption. But scattering from scattering you don't have a loss of energy, this is just a redistribution of the energy. Okay, scattering is just redistributing the energy, but there is no loss. The only loss is come from absorption here. So if there is a flux of energy, if there is a kind of, if the diffuse light moves somehow, okay, this is because we have some absorption somewhere in the system. Okay, so that's the conservation of energy. And surprisingly, actually, we cancel completely the scattering effect. Okay, so we keep this equation on the side. Okay, we will use it at the end. Okay, so, but that's the zero moment. Okay, that's we're just integrating the radiative transfer equation. Okay. Any question? That's the simplest case, okay? So if you're not with me with that, I prefer to explain it. It's okay? Or, yeah?
Why does it happen physically?
What do you mean?
That it cancels out.
Ah, that's what I'm saying, is that this is simply an energy conservation equation.
Just energy conservation.
And scattering does not, it's not a loss of energy, it is just a redistribution of the energy, right? But in total, in the whole volume, you still have the same energy. The only source of loss is the absorption inside the material. Okay. Question?
It's a technical question.
Yes.
In the second term, you came out the nabla out of the integral and
yes.
Right, but and call it Q of omega.
Right. It's not I call it, it's because we just recover
yes,
the expression of
but
Q.
The gradient is on the L.
Right. The gradient
when
is
you put it out, it's only on U.
No. Because it's only on R, I can take it out because the integral is only on U. The omega is just integrating over all direction, possible direction. So U and R, they are completely independent variables.
Okay.
So I can take the
derivative
of R outside.
Okay,
so that's a good question. I really work hard not to have something like this like hidden under the carpet. You know, I try to solve all the problem there. But this one is okay. It's very difficult because you go from one book to another book and you get different notation, different conventions, and it makes the story quite difficult. But at the end. Okay, so let's go to the next step in the approximation, what is called the P1 approximation. So the P1 approximation is a way to go from the full radiative transfer equation to the diffusion equation. So the idea is to assume that the specific intensity is almost isotropic. Okay, so we'll see that the specific intensity can be written as the sum of an isotropic term plus a small anisotropic contribution. Okay, so that's how we are going to introduce this successive expansion in the specific intensity or the radiance. Okay. So that's it. So physically, the radiation is almost isotropic with a small preferred direction. Okay, so that's the picture that I show you at the beginning. Okay, that's the idea. Okay, so let's start with the phase function P. Okay, to establish this first to set this approximation. So where am I here? Oh no, okay. So that's the condition first, okay. So we consider a scattering medium, okay, and those are the conditions that we want to be in. So first condition, let's assume that absorption is negligible, okay. When I say that LA is much larger than LS, it means that what dominates is scattering, okay, not absorption, okay. So I want to have a medium that scatters a lot the light, okay. So that means that the albedo is close to 1, in other words, okay. So let's assume that absorption is almost negligible in the system, okay. Second point, let's assume that we are in a regime of multiple scattering, okay. LS is small compared to the size of the system, so we have many scattering events before we get out of the system. And because of that, because of multiple scattering, the specific intensity tends to be isotropic, okay. So it's possible to find a decomposition of the specific intensity in the sum of an isotropic component and an anisotropic correction. Okay, so that's the idea behind this expansion here. Okay. So first, let's start with the phase function. I always forget this name. The phase function P. Okay. So you remember that P, because of rotational symmetry of the system, okay, P of u prime is actually P of u times u prime, or P of cosine theta. It depends only on the difference between the two vectors, the angle between the two vectors, and not on their orientation. Okay. So this simplifies a lot the story. Okay. If we can assume that we have rotational symmetry, that means that we are not dependent on phi. Okay, phi is the other angular component. Okay, we have an axial symmetry of the problem. Okay. So if this is the case, then we can show that that the phase function can be decomposed over the Legendre polynomial Pn of cos theta. Are you familiar with the Legendre polynomials? Yes, really? Okay, cool. Good. So so this is typical. Actually, when you have an axisymmetric system, okay, and you want to decompose it over the spherical harmonics, okay, actually you need only the spherical harmonics with L non-zero and M equals 0. Okay, you can ignore, actually, you can assume rotational symmetry, so you ignore the M term, so you take only the M equals 0 term. Okay, and that's actually the Legendre polynomials. Okay, so when you consider spherical harmonics, Legendre polynomials are the spherical harmonics for M equals 0. We'll see that later. Okay. So P of cos theta, so the phase function here can be written as an expansion in terms of the Legendre polynomials, okay, which I wrote here. So that's just a convention, the 4 pi here, okay. But the general expression is the sum for all value of L of 2L plus 1 over 4 pi, Pn, a coefficient here, times the Legendre polynomial, and we know these terms. Okay, the first one is 1. Okay, so it's a function between minus 1 and plus 1. Okay, so the first term is 1. Okay, a constant horizontal line between minus 1 and plus 1. Then you look for the function that will be orthogonal to this one. Okay, so actually that gives you a cosine theta. Okay, because there is a negative part and a positive part. Okay, that will cancel the first time. So that's the way you calculate them. You always take the new one, and it has to be orthogonal to the other ones between minus 1 and plus 1. Okay, so let's just consider only the first two terms, P0 equal 1 and P1 equal cos theta. Okay, and the coefficient Pn here are given by this equation. So 2 pi integral from minus 1 to plus 1 of P cosine theta times P of n, so the de Legendre polynomial, cosine theta, so that's by definition of orthogonality of the functions. Okay? So from there, you can calculate P0. You can calculate P0, the small one, the P0 here, okay, which is 1. And P1, look at P1, if I replace Pn here by P1, this is cosine theta. So I have cosine theta times P cosine theta d cosine theta, which is what? Which is the definition of the anisotropic factor G. Okay? So the first term is easy. This is just 1, 1. Okay, so P is 1. Okay, and the second term is G. Okay, the anisotropy factor. Okay, so if I write the expansion of P of cos theta to the two first terms, the first two terms, okay, I have P of cosine theta is 1 plus G, so there is 2L plus 1 here, so this is 3, G times P1, which is cosine theta, okay? So that's the first term in the expansion of the phase function P, okay, 1 plus 3, G cosine theta. Okay, you are with me? Still? Okay. So that's what we call the P1 approximation, where we keep only these two terms. Okay, so with that we can go back to the radiative transfer equation and do, actually we did that last time. So we go to the first moment. Okay, so now instead of integrating, simply integrating the RT, the radiative transfer equation, now we integrate U times the radiative transfer equation. So you multiply the radiative transfer equation by U, the vector U, each term, okay, and you integrate over all space. So that's the first moment, okay. Before we did the zero moment, that's the first moment, okay. So by doing that, the first term here, you recognize Q, the flux, the radiative flux, U times L, integrated over all space. That's good, okay. Second term here, that's the complicated one, okay. So integrate over all space, U times U, nabla of L, d omega, okay. And on the other side, you integrate UL. So again, we have Q here, the flux times mu s plus mu I, okay, plus this term. So what can we do with this term? So I'm integrating here U times all this integral d omega, okay. So again, I can switch the two integrals, okay. I can put the external one inside. So I have integral over 4 pi of U times P of U prime d omega, okay, because I multiply by U and then I integrate over d omega, okay. So now let's use the expansion, the P1 approximation for P, okay, for the phase function. We said that the phase function is 1 plus 3 G U prime, right? So let's see. First term, 1 here. So it's integral of U d omega. What is integral of U d omega? You integrate the vector U, unit vector, in all direction. You get?
4 pi. 4 pi.
No. For each vector U, you have another one which is opposite. So when you sum them, it's 0. So in any direction, you get 0 actually. So the sum of U d omega is 0. Okay, so this term disappears. And we are left with this term here. Okay. So this term gives you 3G U times U prime. Okay. And you can show actually here that this integral is 4 pi over 3 times U prime, okay? So actually that's the integral of u times u, okay? Each component x, y, z gives you an equal contribution, so that's the 1/3 here, 1/3, okay? And the integral over all the volume gives you the 4 pi. So just by hand you can understand why you have this 4 pi 3 times u prime here, okay? So that's good. If I replace that here, then I have 4 pi over 3, so the 4 pi cancel here, the 3 cancel here, okay, with the 3g, okay, and so I have u prime times L of u prime d omega prime, okay, and again I get the q, the flux, okay. So I have g times the flux here times mu s, okay, and you remember that what we wrote last time. So at the end you end up with this equation, time derivative of q plus mu s, so you have 1 here minus g there, 1 minus g, okay, plus mu a times q equal to this bad term here, which is really annoying, this big term here, that we leave for now like that, okay? So you remember we said last time that this term here introduced the transport mean free path. 1 over mu s 1 minus g is exactly the transport mean free path. So that's the transport coefficient, okay, which is the relevant quantity when you consider multiple scattering. Are you fine with that? I say it in like 10 minutes, but it took me hours to really unwrap all these calculations. Okay. Okay, good. So we said that we are in a case where mu a is small. Okay, so if we ignore, or if we consider a system with weak absorption, we can also ignore this term. We'll use that later. Okay, that's a typical approximation here. Okay, so all the problem now is concentrated here. Okay, we got rid of this term now. Now we want to get rid of this term, actually to simplify this term. Okay. So this is where the spherical harmonics expansion will come into the picture. Okay, so we are going to write L here, the specific intensity, which depends on u. Okay, we are going to write it as a first term, which does not depend on u. Okay, so that's the isotropic component of the specific intensity, plus a correction here, which is anisotropic. Okay, so let's put it like that, and let's try to calculate what is this function here. That's really the, let's say, the zero order of it. Okay, then you have other orders. When if you are familiar with spherical expansion, that's typically the basis. So it's a basis over which you can decompose any function on the sphere. So typically L of omega is a function on the sphere, okay, and it can be decomposed, it can be expanded over spherical harmonics. Okay. So the spherical harmonics are the natural basis, complete orthogonal basis on the sphere. So you have like L equal 0, L equal 1, you have M equal 1, minus 1, 0, plus 1, then L equal 2, you have M equal minus 2, minus 1, 0, plus 1, plus 2, and you have all the rest of the things. Okay, so once we decompose it like that, first let's identify the first term here. Okay, so to do that, I propose to integrate over space L on this side and see. So if I integrate L on this side, you recognize again the energy density. Okay, and we'll see on the other side what we have. Okay, taking the integral over the omega. So this term here integrated over omega, you see, q of RT, q does not depend on u, okay? U the omega, q can be taken out of the integral, okay? And again, the integral of u the omega, integral of u in all directions, this is 0, okay? So by integrating this equation, the second term will be 0, okay? What about the first term? So that's simple. Therefore, the isotropic term is directly proportional to the energy density here. So if you integrate this term, L of omega, d omega, okay, so this term is independent of u, so it can be taken out. So it's integral of 4 pi d omega, so it's 4 pi L0. So the integral of L, which is the energy density, is equal to 4 pi L0. So we have an expression for this term. This is 1 over 4 pi, the energy density. Okay? So we can replace easily now L in the equation. If I consider only the first term, I can replace L in the equation by C over 4 pi U of, U is the energy density. There is a C, I don't know where the C comes from. Okay. Yeah, so I didn't see that one. So there is a C, I'm not sure if it's important here. Should be. Okay, so there is again a convention here, which I missed. Okay, so now let's go back to the radiative transfer equation. So you remember here, so we end up with this equation on Q, but on this side, what? We have this term here, this ugly term here. So we are going to replace L of omega by the L0 of omega, simply. Okay, so Q first derivative times this term here. I just removed the mu A, neglected. Okay, and this term here, by replacing delta L by delta L0, we get actually, so it's delta of U, right? So because U is just proportional to L0 of omega, so this delta of U, there is a C term and a 3 here, very important. So I have to check again where the C came from before. Okay. Okay, so that's important equation here. We are getting close to the final one. So if you consider the stationary regime, if you ignore the time variation here in the steady state regime, we have Q is equal to minus 1/3 of C. Here you recognize 1 over LT, the transport mean free path, 1 over transport mean free path, so it comes here. So this is CLT times the gradient of U, of the energy density. So we have here a relation between the flux, the radiative flux, and the radiative density energy here. That tells you that the flux of energy, okay, corresponds to a decrease in the gradient of the energy. Okay, so if you have a gradient, okay, that gives you a flux. Automatically, you have a displacement of the energy. Okay. So in other words, the radiative flux vector is proportional to the gradient of the energy density. And this reminds us a well-known law, which is called the Fick's law, which is related actually to the Ohm's law. Are you familiar with the Fick's law? No? Never heard of that? So the Fick's law actually is not more than the Ohm's law, which tells you that the current G is proportional to the field, Okay, so G is sigma E, or so you see here, the current is the flux here. Okay, there is a constant term here. It's proportional to the gradient of phi. Phi is the potential. Okay, and then gradient of phi is minus gradient of phi is the field E. Okay, so G is proportional to E via sigma. Sigma is the conductance. Okay. So the coefficient of proportionality, and that's the important term here. This term, 1/3 of CLT. This expression, this is the definition of the diffusion constant. Okay, so if you have heard of the diffusion constant, so that's a macroscopic quantity to describe the scattering medium. Okay, and it is proportional to LT. Okay, the transport mean free path. Okay, 1/3 here because we are in three dimension. If you go to 2 dimension, that will be 1/2. Okay, so this is a dimensional term. 1/3 CLT, where C is the speed of light. Okay. So D actually is related to the time domain. If you consider the propagation, the diffusion of the light inside the system over time, okay, the velocity, if you want, is D. So it goes like square root of time, so it's D, or I think it's square root of dt. Okay, so the expansion, we'll see that at the end, the expansion of the diffusive light inside the system, it slows down. Okay, it's not like, it doesn't go like C time t, okay, and you can see t like for direct light, but it goes like square root of time, okay, and the coefficient is d. So d, I think the d is inside, so it's square root of dt. Okay, so that's the way, that's the expansion of the diffuse light. So it goes much slower. If you remember the movie that I showed you, the simulation at the very beginning, the first day, okay, you see that the wave starts from the center and expands, okay, but it's not ballistic, it doesn't go fast, it goes slowly because the time is reduced by a power 1/2. Okay, so this characteristic of the diffusion in 3D space, okay, with this coefficient. What else? Here, okay, that's going to 8. Okay, so here, okay. So from the equation, so now we have 2 equations. We have the first one that we got from the 0th moment, you remember, which is the conservation of energy, okay, and we have this new relation here, which is the relation of Q, the flux relative to the energy, that are proportional. So we can mix the 2 equations. Okay, so I go back to this equation that we got from the zero moment, okay, which is the conservation of energy, and I can replace Q here by the energy density U, okay. And now if you do that, so if I use this equation to replace Q, so you have delta here, I mean the gradient of U. So it's going to be the gradient of U, gradient of gradients, this is the Laplacian, right? And this is the final equation that we end up here. So the variation of U over time is equal to minus D, the diffusion constant, times the Laplacian of U, plus mu a c u RT. Okay, if we neglect the effect of absorption, okay, so we have only these 2 terms here. Okay, I forgot to stop. You didn't tell me anything. What time is it? So I finish with that, and then we make a small break. It will be very short. I mean, I will be almost finished. Okay, so the radiative energy density obeys here a diffusion equation. Okay, this is the same type as the heat equation. I don't know if you see it here. So the heat equation is du over dt. Du over dt. So U is the temperature, for instance. So dt over, so temperature, derivative of the temperature is alpha times the Laplacian of U. Okay, and alpha is called the diffusivity of the medium. So how the heat diffuse inside the system. So this equation is much simpler than the radiative transfer equation, so much easier to handle. Okay, this equation is very important. It is really the basis of many imaging techniques in scattering media. So it's largely used to get information about a scattering medium. Okay. It's important to see also that the Laplacian here is independent of the choice of coordinate. Okay, this is actually an operator which is invariant in translation and rotation. Okay, and the last thing that we can say is that if we consider the stationary regime, if we ignore the time variation here, you end up with a very simple equation. Oops. Yeah, so we end up actually with what is called the Laplace equation if you consider the stationary regime, which is Laplacian of U is equal to 0. Okay. So that's the case of stationary equation. So very simple equation, Laplace equation. Also largely used. Any question? So you understand the derivation, or essentially the idea. Okay, the idea is really to consider the radiative transfer equation, considering the zero moment of it, so by integrating the equation over all direction. Then the first moment, which is integrating U times the radiative transfer equation. Okay, and from these two equations, and by taking the expansion of the specific intensity in terms of spherical harmonics. Actually, we take the first term. Okay, we get actually the simple expression, a relation between Q and energy. Okay, and this relation is injected into the energy conservation of the zeroth moment, and we get the diffusion equation. That's all the story. Okay. Okay, so there is no question, so we make a small break.
Because of light, they move here.
The light reflection.
Okay, so I mean, with that, I just want to show you an illustration of what we can do with the diffusion equation. And we will end this course with the discussion on the random walk. Okay, so we are here, yes. Oh, I lost the screen. Okay, so we end up with the diffusion equation, and the special case for stationary waves is the Laplace equation. Simply Laplacian of U is equal to 0. Okay. So what can we do with that? A very simple example illustration for that. So let's take the example of a diffuse behavior. That's the case of a slab. So we're going to take a slab of scattering medium. Okay, light will come from one side, and we will look in transmission on the other side. Okay, So it's really a one-dimensional problem. Okay, so that will even be even simpler because it's a 1D problem. So we consider propagation of a monochromatic plane wave in a scattering and non-absorbing slab. So let's assume that it's not absorbing. We can neglect the mu a, the absorption coefficient, and the slab is between z equals 0 and z equals 8. So the z-axis is perpendicular to the slab. Let's assume that the scattering mean free path is small compared to the thickness. So L is the thickness of the slab. Okay, so we have many scattering inside the system, and more than that, also LT, the transport mean free path, is smaller than L. So that's the diffusion equation. Okay, so actually this is something to remember. Multiple scattering is when the scattering mean free path is smaller than the size of the system, and diffusion approximation is when LT, the transport mean free path, is smaller than the size of the system. Okay. So let's assume we are in those conditions here. So the diffusion equation in the stationary regime becomes the Laplace equation, delta U equals 0. U again is the energy density. So that means that the second derivative of U along the z-axis is 0. So you integrate, this is a constant. Okay. The constant is given by the Fick's law. We saw that before, okay? So the U over dz is minus Q, the flux, divided by the diffusion constant. Okay? And you can integrate another time, where Q is the relative flux vector, okay? And you can integrate a second time, and this time you get, so how does it work? So d over dz is equal constant, and you integrate another time. So Q, I'm lost here. So the constant Q d over dz. So what did I do? It was Q times S. What is S? Oh, in integration a second time, one gets the flux through the surface S. So this is just multiplying after that. So Q is equal to d. So to d over L, the energy at position 0, because there is a minus here, so it's the energy at position 0 minus the energy at position L, okay? And here what you recognize, if you multiply by S, by the surface of the slab, you recognize here the flux through a surface, that's the current, okay? Is equal to here a variation of potential, okay, over a constant which is given by this constant term here, okay. So actually you recognize the standard equation mu I equal U over R, okay, and if you write by analogy with the Ohm's law, that gives you a conductance which is given by D, the diffusion coefficient, times the surface divided by the length, the thickness of the slab. Okay, so you see that G is proportional to D is proportional to LT. So G is proportional to the transport mean free path. Okay, so that's very interesting. Here we define the conductance, which is a quantity that you are familiar with in electronics. Okay, here we describe that as, so that's for optics, but it's the same for electronics. Okay, you can see the electrons as waves propagating the scattering medium. Okay, so the conductance that you would measure in a circuit actually correspond to the multiple scattering proportional to the transport mean free path. And what is interesting, this is inversely proportional to N. Okay, that means that the conductance decreases as with L, as with 1 over L, inversely proportional to L, as you increase the thickness of the slab. So the conductance is inversely proportional to the thickness of the slab. Okay, so that means that in our case, if we look at the transmission through the system, so transmission for length L is proportional to 1 over L. Okay. And this is characteristic of the diffusive regime. When you are in the diffusive regime, as you increase the size of the system, the transmission decreases as 1 over L. So what does it mean? If it decreases, where is the energy going? My question. Okay, you have light coming inside your slab. Okay, and at the output, T of L is reduced by 1 over L. Okay, so where is the energy gone? Any idea? You understand the question? You have transmission which is reduced by 1 over L. Okay, so that means that part of the energy does not cross the system. So where is it? We said that there is no absorption. We assume that we are in a case where there is no absorption in the system. Heat? No, heat would be a kind of absorption effect, right? Light that goes through a piece of paper or through the wall here, okay? The light that goes through the wall, the paint is a scattering medium, strongly scattering medium, okay? So the light goes through all these particles there, okay? It is strongly scattered, and the intensity decreases in transmission as 1 over L, okay? But where is the light? Where the light is gone? If you look at the wall, where is the light?
The energy go to heating? The energy go to heating?
To heating? No, we assume that there is no absorption.
Oh.
Purely a scattering medium. So the energy is just reflected back. Okay? The photon they want to penetrate inside the system, okay? But it decreases as 1 over L because most of the photon they will be reflected back by the system. And what you see when you look at snow, you look at a piece of sheet of paper, or the paint on the wall, what you see actually is all the energy that cannot penetrate inside the system, which is reflected back by the system. It's not a reflection by the surface. It's because of multiple scattering. Most of the light will exit back in all directions. Okay? In reflection not reflection, in the back, I should say actually in backward direction. All the light comes back in backward direction, most of it that cannot penetrate inside the system. Okay? So that explains actually the color, the white color that you get from snow, from a glass of milk, or a sheet of paper. Okay, so that's a very simple usage of the diffusion equation, of the Laplace equation in that case, to show simple relation like the Ohm's law. Actually, you get the Ohm's law directly from there. Okay. So because it's a very general equation for heat, for electronic conduction. Okay, this is a very broad, I mean, it addresses many problems, not only photons. Okay? Any question for this example? Okay. So I want to finish by introducing the concept of a random walk, okay, which exactly reproduce actually the diffusion of any phenomenon, diffusion of heat, diffusion of light, diffusion of molecules in gas, the Brownian motion, for instance, in a liquid. Okay, so what is the random walk? So you take a coin, you toss a coin, okay, and if its face you move to the right, and if its tail you move to the left. Okay. So that's the random walk on one dimension, okay? Either move +1 or -1 with equal probability. Okay. So after some time, after many steps, if you look at the region that has been explored by the random walker, you get something like that. Actually, it's a Gaussian distribution. Okay. Most of the time, the random walker comes back to the initial position, maximum probability. Okay, but it will explore larger and larger regions. Okay, so this Gaussian actually with time will expand. Okay, and the width of the Gaussian expands like square root of time. Okay, so square root of the number of steps, if you prefer. Okay, so that's typical of diffusion. Okay, diffusion goes like square root of time with a coefficient which is d, the diffusion coefficient. Okay, and these apply to many fields. It's applied to the stock market. There are even like sculptures like that in London, where they have kind of a 3D simulation of a quantum walk made out of wires. Okay, so if you look from far, you see this distribution. Okay. What is interesting in the random walk, I mean, there is a lot of theory just by considering random walks. What is very important in this field is the dimensionality of the problem. Okay, so usually it's called the random drunker. So you have the problem in one dimension, as I described it. Okay, you can go left or right. Okay, so here going up or down. Okay, and over time, you can have different trajectories. Okay, and there is this expansion here. The expansion goes like square root of time. That's one dimension. You can have it in 2 dimensions. Okay, so you can have a 2-dimensional random walk on a regular lattice. Okay, so you have like 4 directions to choose 4 with equal probability. And what is important related to what we discussed before is that the step of the random walk is the transport mean free path. Okay, so transport mean free path tells you that over one mean free path I'm just going straight. Okay, because I have like forward scattering. But after one mean free path, I change direction. Okay, so I lose the initial direction of propagation.
That's a simplification.
Yeah, very very crude simplification. But that's the I will give it with more precisely. But that's the characteristic length that comes into the picture when you consider random walk. Okay, so the walk is done. Each step it's one transport mean free path. Okay. You can have a 2-dimension random walk with also random direction. Okay, so you can choose randomly the direction that the walker takes. Okay, so starting from this point, you can explore different regions, and there is a lot of mathematics around that. 3-dimensional walk, random walk. Okay. So why do I show these different examples? Because 1D, 2D, and 3D have different, can give different results. One important, so let me first introduce, before talking about dimensionality, I want to introduce you to what is called Monte Carlo simulations. Monte Carlo simulation, okay, this is actually that's something that you may meet in the future. There's a very standard method to describe transport of light or any particles like Brownian motion or whatever. Okay, so the idea is like that. So actually you reproduce directly the radiative transfer equation. So a photon travels straight for a random distance s. Okay, so instead of taking simply LT, transform mean free path, you can take a probability distribution here, S, okay, with the characteristic length which is LT. So mu T exponential minus mu T S, okay. So that will give you the probability to make a step of a given length S. After one step scattering, okay, the object, the photon or whatever is scattered in a different direction. So at each scattering event, the direction is chosen by the phase function. Okay, so we know that the scatterers has a phase function p of cosine theta. So we use this phase function to redirect the photon in a different direction. And you repeat that many times and for many photons. Okay, and that gives you a very nice description of light transport in the scattering medium that you define. Okay, so it's a very powerful tool, simulation tool, very simple to implement. Okay, and very accurate actually. This is really a statistical model. Okay, to describe the propagation. So Monte Carlo simulation, and I will finish with that. So there is an interesting property of random walks is the question of return probability. What is the probability for the walker to come back to his initial place? Okay, and surprisingly, you have different results for 1D and 2D and 3D. Okay, in 1D and 2D, the probability of return is 1, and in 3D, the probability of return is 0. Okay, that means that there is no chance for a 3D walker to come back. So I wrote it like that. A drunk man will find his way home all the time because he's walking on a two-dimensional space. But a drunk bird may never come back home and will get lost forever. Okay, so why do we have this difference? You have any intuition for that? So the two dimension is really a marginal dimension. Okay? It takes like infinite time for the walker to come back home, but he will, at the end, he will come back. So if you take in one dimension, okay, in one dimension, so actually for any dimension, the space explored by the walker increases like square root of time. Okay. That's general. It's true for 1D, 2D, 3D. Okay, so the growing the space explored by the walker goes like square root of time. Okay. Now, what changes between 1D and 3D is the volume. Okay, so for a distance square root of t. Okay, in 1D you have, I mean, it's linear. Okay, so it goes like r. So it goes like square root of time. Okay. For in 3D it goes like power 3. Okay. So actually it's t to the power 3 half, 3 over 2. Okay. Okay. If you consider what happened during the time t. Okay. So t in 1D during time t. The walker explore square root of t, so t over square root of t is square root of t. Okay, that means that he will not miss. I mean, he will come many times to the same places. Okay, so among them the initial place. But in the 3D case, you have t over t to the power 3 over 2. Okay, so the inverse is. So it gives you t. It gives you yes. So it's 1 over square root of t. For 3D, you get 1 over square root of t. Okay, so when t becomes large, the probability of return goes to 0. Okay, and for 2D, actually it's t over t because it goes like the square, and it's 1. So actually there is I mean, probability of return is possible, but it takes like an infinite time. Okay, so that's the way to understand that. This will be very important for the following. Okay, remember this characteristic here of the random walk. We will deal with that probably next class or maybe in 2 classes on that topic. Okay. I want to mention one last thing here, one also interesting thing. The probability for 2 walker now you take two walkers, okay, random walk. What is the probability? So they start from the same starting point, okay. What is the probability for them to meet again? It's okay. So I wanted to ask you the question, but the answer is here. It can be shown that the difference between the location of the two independent random walks is also a simple random walk. Okay, so the difference of position is also random walk. Okay. So same result. In 1D and 2D, they will meet again. In 3D, they will never meet. Okay. Yeah. Okay. Any question on that? So I think it's a very interesting tool. It's like instead of equations, you have a very simple model to describe a lot of physics actually in this case. It's mostly used numerically to model the diffusion. Okay, so with that I'm done. Thank you.
Thank you.
And so we don't meet next week. Yes, next week is Hanukkah. And I want to cancel that. So we are supposed to. There is no break on that day, so it's on Monday. But I want to. It's too late, so I won't be able to give you this course. But we have still 4 courses. No, more than that, I think. So we have like 2-3 more courses, more oriented to strongly scattering system. We are going to talk about weak localization, Anderson localization, okay? So we are going to, from what we learn here, we are going to put back the effect of interferences, okay? That is completely ignored here, okay? You see the Monte Carlo simulation model is just a walk without any wave effect. So we completely ignored the wave nature of light. So we are going to go back to that, and I will show you that actually you cannot neglect the wave nature of light, and it gives very interesting effect. So we go to things that are more into research. So less equation, more qualitative, but I think very interesting. Okay, so I will also put, I hope this week, I will put on the Moodle papers that you can pick up, that you can choose. Okay, once a paper is taken, I will remove it from the list. Okay, so don't wait too late if you want to take something that you like to take. So you have time to prepare. Okay, and the last two sessions, you will have your presentation. Okay. And, I think with that we'll cover most of the topic. Okay, so thank you.
Thank you.
And see you in 2 weeks from now. I will send a message because I'm not sure everyone remember that.
How long should be the presentation?
I don't remember how much. I think like 20 minutes, something like that. 15, 20 minutes. I have to check my schedule. I will write all the instructions.
差不多吧，我不太确定。
是每天是到
好几天，5、6天啊。
那我不那接了，那还是得过来。就是他那估计会过来。
哎，你什么节都来？
对啊。
他月节都来，月
节他就是节日他不来。
就那一天不来。
对，所以我就说如果放1天的话，肯定不来。
那好几天。
好几天，那肯定天天
包不过来。他们也很传统的，其实他包不过来。
下周上。
我不知道，你看邮件，我不确定。不是，他应该还没发，他肯定会发的。
后面会说的。
对，他会说的。
开始说那个是要做 paper。
不是，
就是选一个 paper， 然后展示 presentation。
最后2节课。
最后2节。
他有说每节课多少时间？
我没听到。
应该有写。